Hey guys, this is part 2 of today's lesson. We're just going to go through each of these problems. Hopefully you've already attempted them, but if you have some questions or just don't know where to start, hopefully this video will help you understand that, okay? Alright, so let's start with the first one. We have a 500 ml flask that is filled with krypton at STP. How many moles of krypton are present? And calculate the density of krypton at STP. So this is actually a two-part question. Here, the first thing that we need to do is get from milliliters of krypton to liters. And we do that by just dividing by 1,000. All right, I know that's 1,000 milliliters in 1 liter, so the milliliters will cancel. You could have also done the King-Henry method and just moved the decimal 1, 2, 3 places. You'll arrive at the same answer. All right, now the next thing I need to know is how many moles. All right, the only thing that I can use at this particular point is my molar volume. My molar volume connects the moles and the liters, and that's the reason why we had to convert it from milliliters to liters. That's the other thing. All right, just to kind of think about. All right, and so I'm going to use my molar volume of 22.4 liters to get that, to make that happen. And so my liters here will cancel out, and I'm left with moles. And 500 divided by 1,000 divided by 22.4, because it's at the bottom, gives me 0.02 moles of krypton. Okay. The second part of that is to calculate the density of krypton at STP. Now, density is equal to the mass divided by the volume. But in this particular chapter, you may have noticed that I've been doing the molar mass and the molar volume. So it's the same concept, but we're just arriving at it a little bit differently, all right? Or using the information a little bit differently. And so the density for krypton can be found, or excuse me, the molar mass of krypton can be found on the periodic table, and krypton's molar mass is 83.3 grams per mole, and of course we know the molar volume is 22.4 liters per mole. My moles are going to cancel out, and I'm left with grams per liter, and I just divide 83.8 by 22.4 to get 3.74 grams per liter. Now technically I only needed one sig fig because there's one here, and so really my final answer should be 4 grams per liter. So I would lose 1 point. Just be careful of the sig figs on the quiz on Friday, okay? All right, so that one is all set, and this one has 1 sig fig, so I'm good there. I wouldn't lose any points on this one. This next question says a weather balloon contains 10 liters of helium at STP. How many moles of helium are present, and calculate the density of helium in STP. This one again is done the same way as the previous example. We're going to start with 10 liters of helium, and the nice thing is I don't have to convert from milliliters to liters. It's already in liters, and I'm going to use my molar volume of 22.4 to get from liters to moles. Now the question that you may be wondering, like, why are you using 22.4? Like, do I always use that? The reason why I know that I have to use 22.4 is because it's at STP. Remember, one of the things that I said to look for is that term or that phrase, at STP. So that's the only time that I could really use that. And of course I'm going between moles and liters anyway, so that's also helpful. My liters will cancel out, and I'm dividing 10.0 by 22.4 to get 0.446 moles of helium. All right. Now the second part of that is the density. Density is still equal to the molar mass divided by the molar volume. The molar mass in this case for helium is going to be 4.002, and the molar volume is still 22.4 liters per mole. All right. So my grams and my moles are going to cancel out, and I'm left with grams per liter. 4.003 divided by 22.4 gives us an answer of 0.179 grams per liter, which is perfect. Now, both of these have 3 sig figs. I started with 3 sig figs, so I am good to go there. Okay. Now, neither one of these questions, number 1 or number 2, really had anything to do with the ideal gas laws. They were more practice with the density and even using the molar volume, but hopefully that was good practice for you guys. This next one here, let's see if we're going to be using the ideal gas law. So I have a liter, I have a 1 liter flask that's filled with argon by water displacement at 20 degrees Celsius. The atmospheric pressure is 750.6 torr. After correcting for water vapor, in the flask determine how many moles of argon are present, and what is the density of argon at STP. So again, this is a two-part question, and let's see. Can we use the ideal gas law? Yes, we can use that equation. We have pressure. The pressure is 750.6 torr right here. Do we have volume? Yes, it's 1 liter right there. Do we have the number of moles? No, we don't. That's what we're trying to figure out. Do we know what the R value is going to be, the gas constant? Well, we don't necessarily know, but because I have a unit of torr, I'm going to use the gas constant that also has torr in its unit. And then, of course, my temperature is going to be 20 plus the 273, 293. All right? So, because I'm looking for N, I'm going to rearrange some things, divide both sides by RT, and my working equation is PV over RT. And then I just plug in my numbers here. All right, my pressure, my volume, my gas constant, again, the gas constant that contains torr as a part of its unit, and then my temperature there after I've added 273 to that. So my torrs are going to cancel out, my liters will cancel out, and my kelvins will cancel out. All right, and I'm left with a unit of mole, which is good because that's what I kind of need. All right, and so 750.6 times 1 divided by 62.36 divided by 293 gives me a really big number, but I need only 3 significant digits because I have 3 here, I have 4 here. This, although it is precise because it has a decimal, I still don't factor it in. In any case, it's still 3 sig figs. So I'm using that as my final answer to determine my final answer. 3 sig figs, so that rounds to 0.0411 moles of argon. The second part of that is to figure out the density. The density is done the same way that the other 2 examples were done. Density is equal to the molar mass divided by the molar volume. And the molar mass of argon is 39.95, and the molar volume is still 22.4. So I'm going to divide the molar mass by the molar volume. My moles are going to cancel, and I'm left with 1.78 grams per liter. Again, I have 3 sig figs, so I don't lose any points on this problem either. I've done it correctly. All right, and then this is the last one. I have a tank of oxygen that contains 89 grams of oxygen. If the volume of the tank is 7.5 liters, what is the pressure of the oxygen if the temperature is 21 degrees Celsius? And we know that we're using the ideal gas laws because I have it up there, but even if you didn't, you kind of go through to see if you have the things. All right, pressure. I don't know what the pressure is, so I have to kind of put a pin in that. My volume. I do have a volume. Do I have the N? I do not have my N, my number of moles, but I have a way to get to it. I know that I have 89 grams of oxygen, so in order to get to the number of moles, I have to use the molar mass of O2 to get there. Okay, same thing that we did in Chapter 9, we're doing it in Chapter 10 as well. And then my temperature is to 21 plus the 273 to get my Kelvin. All right, so let's go ahead and get my grams to moles. All right, so again, I need to use my molar mass of O2. Oxygen is 16, but because it's O2, it's a diatomic element, I have to multiply that by 2, so I'm using 32. 89 divided by the 32 gives us, my grams are going to cancel, and it's going to give us an answer of 2.78 moles of oxygen. Okay, so that's the number that we'll substitute for N. Now going back over here, I need to figure out pressure. If I'm trying to get pressure by itself, I need to divide both sides by V, and when I do so, I have P is equal to nRT over V, which works. All right, and so I plug in my numbers. My N is 2.78. My R, I could have chosen any R value, any gas constant. The reason being is I'm looking for pressure, and because the pressure, the gas constant is dependent on the pressure, and I'm looking for pressure, I could have chosen any of them. I decided to use the 0.0821 just because I like to use atmospheres. I do. So, but you could have done anything. Unless I specifically say what is the pressure in torr or whatever, then you can choose whichever one that you would like if you're looking for pressure when using the ideal gas law, okay? And then, of course, my temperature is 294 Kelvin, and I divide all of that by liters. So what's going to cancel out? My moles are going to cancel out, my liters will cancel out, and my kelvins will cancel out. And so I know I have a unit of atmosphere. And you just plug and chug 2.78 times 0.0821 times 294 divided by 7.5, I get 8.9 atmospheres. And that's it. So the ideal gas law is not as challenging as you think it would be. As long as you have all of the information that's provided, you should be good to go. And you see the different scenarios. Some are very straightforward. It's already a number of moles, and some of them you have to put a little bit of extra work in there to kind of get started to use it. But hopefully the examples make sense for you guys. Okay? All right, see you guys later.